down here, and 400 and I don't want to mess up too much. I know. And 459 kips on the far end. So we have less clamping force down here. This again will allow for deflection from here out. So from this point to here, I need deflection in the deck. Remember, and I'm developing deflection in the deck by showing you that this end of the deck is structurally weaker with post-tensioning than the other deck. I've showed it twice now with the C2 and D1 compared to one end to the next. You can find it in the drawings also under your dead and live ends. Rotating around, so let me finish the theory on this one then. So then they finished post-tensioning these guys. Then they moved on to D2 through D6 in the deck. Then they did C4, I believe, right? That was next, C4. Let me confirm that. Let me look at the drawings here, and give me just a moment. I don't want to stop the video, so you're going to have to bear with me. You have to bear with me on the video content. Scrolling down the page, okay. So I'll bring you over here. Yeah, sorry about that, movement like that, but hey, that's what we have. Guess you guys just seen one of my models on my computer. I might as well go and give it to you. It says, lack of planning on your part does not constitute an emergency on my part. Okay? You're eating an elephant. Relax and enjoy the moment. That's with anything in life. Whatever's big, take your time, you know. It's going to be, if it's a project, it's going to take as long as it takes. This is 1.5 years now, right? So, for example, that. But this is very important. Lack of planning on your part does not constitute an emergency on mine. This is what ultimately I get drug into, people's emergencies, and I'm like, you know, that's not my it's not the way I'm going to handle it. It's your emergency, not mine. So I'm going to take my time. So now right here it says stress deck longitudinal tendons D1, stress canopy tendons D2, so C2. Stress post-tension bars in 2 and 11. Stress deck longitudinal tendons, so there's D2 through D6. And then stress bottom slab transverse post-tension tendon, alternate ends stressing is required for the transverse tendons. So they work from one end to the other end, back and forth, you know, 1,000,000 times. These are spaced 2'6", 2'8" apart. It's 2 inches difference. It's nothing worth anything as far as I care. At this time. Stress diagonal bars in 3 and 10. At this point, the canopy is still not completed. They're now putting loads on the diagonals now, pulling down on the canopy, and lastly, they stress tendon longitudinal tendon C3, and that's the canopy. So they did C2, and lastly they did C3. So C3 has got to get this elongation, has the most amount of forces and theoretical forces to overcome. I would love to see the elongation on C3 compared to C2. This is so critical. This is data that I think it would be awesome to have. Because C2 and C3 are the same lengths. They clearly should require the elongation should be the same on each one of them, if theoretically everything worked out with zero wobble and etc. Zero wobble. Temporary supports of main span section shall stay in the middle of the cross section during SMPT transportation. I talked about that many times, that during transportation, that means if that's staying there, they're not saying remove and put back. They're saying temporary supports should stay in the middle. Well, obviously that didn't take place, and they went with 11. And I think that's a financial decision, because to break down all that temporary scaffolding between the canopy and the deck might have had called for road closure for safety issues. You know, the piece of scaffolding could fall down the road. And I think that's ultimately how we got to where you see 11 and 2 with bars now, and this is not being followed. I'd love to see that addressed in an OSHA report or an NTSB report. Why did they deviate from there? When and who authorized it, and why? Why did we get the okay? So moving on. Oh, that would have eliminated uh, um, 11 and 2 having post-tensioning in them, but on the basis that it was only done for transportation. But you can see the conflict in these notes, that it's applied here in 2 and 11, and also it's here under scaffolding. Temporary supports of main span section shall stay in the middle of the cross section during SMP transportation. Temporary supports. I saw no temporary supports during transportation, not even a single bar. Going back to, it looks like I might be ending the video soon. It's got 29 minutes, it says. Going back to, let me just go down to the end here. I'm trying to do a little bit of I know I'm taking some liberty, guys, so any engineers out there, I'm taking some liberties, but I took it back in the comment section. I make it clear what I'm doing. And if you're an engineer, well, then you know that grouted, bonded, and ungrouted is a big difference as far as post-tensioning goes. It's like the books. You know, you're holding two books together, a series of books. Here's unbonded, if you will, just using compression from the post-tensioning of the two ends. And I'm holding the books together. Well, it's great. If I release any right hand, if I release my right hand, all the books fall with that way there. But you would have ductwork in there. It would still fall to the ductwork. It would only fall down to the ductwork, and now it's the cable will still, the tendons will have a way of holding it back if I did that. So theoretically you saw that, but you had no bar between there or no tendons. So the tendons are actually pulling apart, which creates a force inwards. But I'm understanding, I'm showing you the book way. But if I release my hand in the book, it's just this invisible force, all the books fall. And in this way, if I release my hand, the cables will catch the books. Same as this, that when they detensioned number 2 and 11, that they detensioned, let me make sure I can see the video good. They detensioned A and B. A is in the deck, B is out here. At that point, just like the books thing, it cracked like hell. It cracked like hell, but it didn't go all the way down to failure, total failure, ultimate failure, because of these bars were still in place. They grab hold. That put a load back in this canopy. To grab hold, it has to be grabbing from the canopy at that point. That means when they loosen this up, these are no longer loose anymore. They are snug, and they're holding up, I believe, they're holding up more than just the cracks in the what they call punching shear. If you wanted to go down that road, calling it punching shear, I can go down that road for this example, and I can go down my road also. Punching shear just has it going downwards. But remember that it's being stopped, restricted by the A and B, and that's why you see the crack, the shape of the back of the diaphragm with what I call shear cracks. They're looking at it just as a sideways, I believe they're looking at it just as this format. In reality, this has 4 sides to it. All 4 sides are putting down a shear moment, a moment. They're discounted number 12 totally for dead loads, that it has none. I have not discounted it, especially because of the cracks that are open here at the bottom of here. This is why I can't get a punching out of this number 11, because number 11 has now exhibited splits and cracks. It's failed at the end here. Structurally, has no integrity as far as I'm concerned. Has no integrity. So how can it then turn around and act like a punching moment? We have it when they release the loads, they're saying that it's slid across and downwards. Well, this is to scale. This model is to scale. Let me turn it a bit, and I'll use this model instead of that one. I guess I should use that one. I should use a combination of both. But let me move this one out of the way. Don't want to break them. They're quite fragile. They took quite some time to make. So let's go down the line of shearing this off. Make sure you can see in the video. Good. Well, for this to move over, they show in all the videos and I'm going to dial it back now from attacking engineer groups, because maybe they're watching this now and maybe they go, oh yeah, That was stupid, but I don't know if they can. I don't know if they can. This is the problem with engineers, is that there's not many engineers that admit they made a mistake. So you have in the videos, they show the clips. They show this little section here, and they show this sliding off. Well, that's magic. That's magic, because if this is sliding off, first off, the cracks. They don't show the cracks inside there in their videos, which we have crack evidence. Show the cracks in your member and show how it can still slide off. That's one thing. Show this inside the member, how it's pushing through here, because you have it sliding off and downwards. The deck is in place up to here. This deck is still in the place up to here. Some grind out, but if you will, but they have it going that way. Look at the top of the deck here. For that to move, this is still connected. It needs a force to do it. The force would have to have come from the load from the structure. This is before failure. This is before failure that we're looking at. We're looking at the cracks of hell. Cracks from hell. You have to have this, since this is all one piece, and it's anchored with something that would take, they're rated at 400. Let me look at my notes. Those bars are rated at 400 and... Each bar is rated at 400 kips. You would need 800 kips, 800,000 pounds of force to get rid of these two bars. Maybe you could shave one off and then shave the second one off. It didn't happen. We know that nothing sheared across these. These were still in place. They were like this in the failure. So nothing sheared this away. This cannot move because it's attached to the top. You can't just take an image like that and do that. That's magic. It's bad engineering, and everyone with professional engineering license should have to also explain how did it do it with the crack, and how did it move it without moving the rest of the structure. Because they're claiming that it caused that effect. I'm claiming how that effect happened was detensioning. Once they detension, they lost their clamp force of the bottom of the clamp force here. Let me overlay that. Make sure you can see it. Let me zoom in a little bit. Good. So here we got little shadows going on there, but we'll work with it. I'll give you a little bit of an angle, and it might help even, because you won't be able to draw conclusions as fast. You know, psychological stuff. If I do it the other way, you get ahead of it. This way, it's something new. So this is A and this is B, I believe. And we release B and A. A is inside the deck here. This is the deck, out to right there. So that's the deck. Out to here, and then the blister is here. What I call the blister, but it was all poured in one, as I stated. When they released the deck, A, all that did was release the loads inside here. It didn't do much. It probably relieved loads going down 10. And then same thing with this one. When they released this one, it relieved loads going down 10 again. But it loosened this up. They had no idea how much this bridge was being racked and held together by these two members here, number 11 and number 2. But they had no idea how much this kept this bridge together. As we look at, as we look at this grouting, how important it is. We're just on nylon at this point. This has steel in it to some degree inside this diaphragm to help get all the loads out to, well, right now out to this darn nylon. So the point loads are down here on this nylon shim. It's not in the grouted area because it hasn't been done. It's not being held down by the bar because the bar appears not to have a plate on it at this time. So the bar is not holding it down either. The bar is very interesting because it's over in the failure zone, and so somewhere here it's sheared, and we don't know, we're not getting evidence of that. Or they just dropped the bar inside there loosely, and they never cranked it down into, I don't know what's down in here. I don't know how this bar was to interact with this section here. A coupling that dropped down and you threaded it on. Both bars are very interesting. Nothing to cry about this time. Could it have saved the structure? Very possible. Very possible. That would have kept it. It would have saved the structure, allowed people to see it was totally out of control, and I think, and maybe save lives. But back to this one. This should have been grouted. This would have transferred all the loads when they released this. when they release this, the back of the number 10 has a lot of loads on, number 12 has loads on it that allow, okay, right, that have loads on it that's not shimmed, as Denny Pate stated. So it went down, the back of it I showed in the other video, it has the tape measure shows that it took a torque, it took a left and right, it took a rotation. Let me see this way. It took a rotation if you look at the tape measure from the back side. That means that number 12, the whole back of the diaphragm, after it's sheared off, I think the shearing action is coming from a downward force. How do I get there? Well, I have the deck. This crack here is most important. This was appeared many weeks before, or many days before. Let's get to that crack. Let me back out. Yeah. So I'm going to back out to this degree. Let me see if I can get you out of that shadow. Okay, I'll move it over just a touch. Looking at the video. So this crack was because of a deviation in this deck. And remember that this could never, these forces coming down here created a force, I believe when they did number 11, the forces came down and created deflection in the deck being resisted by the 4 bars in number 10 here. And it shows that the, I'm sorry, first the force is down, failure in the scaffolding somehow, and then when it finally released and they went further down the line with the D6, D2 through D6, and at that point I think the engineer might have been on board, the CEI. Well, he waited 6 days, so he came at this late with trying to tell us, making that statement that it was a tensile crack. That was the cause of it, the initial cause. I think deflection's already happened here. If you get deflection down here of any amount, you get a crack right here. This is that like crack, not a shearing going on, and especially that crack appeared after they post-tension number 11. And it's stated in the OSHA report, and the other engineers are stating that this clamp force kept this together. When they released it, it caused the sliding. Well, this clamp force was already applied when you get this crack here. So either you have your distance between these members aren't square. In other words, that this call is 10 foot, but down here it's 9 foot 9 inches. When you compress this, let's call this 9 foot 9, let's call this 10. So 9 foot 9 over here and 10 foot on this side. When you compress this to those forces, it creates that a load down here also because it's no longer square now. So that would create a force down here that really matters. So this distance is so critical with this post-tensioning and transferring of loads also. So that's my other way to show you if this distance wasn't perfect here to here, then that would also create a force down 10 where it was not designed to be, because one is longer than the other. It's no longer acting in equilibrium. So this deflection here gets me my crack here. This is the start of the whole failure. This is indicating that the deck is deflected from one reason or another, whether it be from post-tensioning 2 and 11, because this happened after, this appeared after they did 2 and 11. So this, to me, again, it's only because it got deflection in the deck. Deflection in the deck, because these are tied together, creates a pull down of the canopy, number 2, downwards. Remember, they didn't do 3. C3 is not done until after they do everything else. Even the transverse cables, as I recall. Let me look at my notes, they're right there. Hold on. Yeah, C3 is last. So C3 is last in this whole operation of post-tensioning. They did the transverse cables coming back and forth. Speaking of the transverse cables, when they did this, there was no grouting. Now, you know, I've always been a little nutso about this grouting deal. So 11, D1 and C2 and number 2 were not grouted at the time of this inspection. So that allows for breaks in these pipes, these ductwork, and it's 2.5 inches of it. 2.5 inches of, I think, of this ductwork, of this, and I forget what this is. Nevertheless, there's room for deflection inside this system. void, if you will, inside here. So it's not grouted at this point. Also, there are no transverse cables to help transfer the loads. Now we go back to this guy here. So when they did the, yeah, bear with me please. Bear with me. So when they did, that's a shovel in the background, anybody wondering? If it's distracting, let me move it. So, a little garden up front there. So, if it's distracting, it's gone now. Let's go this angle. Slide down my work there. So I'm taking liberty now because this is not to scale, and I'll try to recall my liberty as I go along. Last thing I want to do is get something technically wrong with post-tensioning, how I'm explaining it. For example, this would be more like a free body diagram that you're looking at when I show you it in this format. In reality, it's compression. The loads are creating a tension in concrete that come down. The post-tensioning predicts where the loads are going to be. It counters the tension that's created by the loads coming down with compression. All right, so that's my disclosure to that. With that said, this looks like it's like a free body diagram where you don't need to go crazy about it. You just simply you visualize it this way, and this is how it would look. Now, I purposely did what you're looking at here. This would be like reinforcement. This does have reinforcement in it. That reinforcement, that mat is 6x6, I think, all everywhere, beautifully so. So you imagine if you were post-tensioning and you had to go across that mat, but you have to resist the mat forces also because the concrete's already been set. Well, your forces, you can see me trying to, I'm actually doing that now. You see what's happening there. I'm creating more force out here, which we know happens in tendons when you're post-tensioning, than in the inside. Because that's where it's connected. All right, sorry, my cat just distracted me. It's not bonded here. These are just ductworks. So it's not bonded there, so that your force, your compression are the two ends. So I don't think I'm being, so you guys can jump in, I don't think I'm being unfair by having the 2 points. The 2 points, my load points, being on the outside. This is not bonded. This is, the compression is created by the outside, which puts D6 under a lot of stress. It's the first one in line, right? The first one that has to cross it. Let's look at over here now. Let's do this. So again, you got your reinforcement keeping this together though, so it would be here again, the reinforcement would stop it. So let's slide it over to the reinforcement, if you will. You can see it's going to have a lot less deformation. You know, for fairness, I need something to exaggerate and show you. And you can see what happens as soon as it passes the concrete, you know, it gets like a little shear moment going on. That's not the way it would look. It would be more in line with this one, which believe me, I've kind of thought this out. I have it all lined up for you. So this would be this is not touching, incidentally. I have a hard piece of, my mat is here, if you will. The foam's tying it all in. That's my intent. Oh, beautiful. This is supposed to be on the other side. Oops. Oops. Anyway.